Yeah. So thank you very much to the organizers for having me. It's really a pleasure to be part of the event. I'm very sorry that I can't be there in person today, but normally I'm local. So if you'd like to chat about anything that I'm talking about today, please feel free to send me an email and we can set up a time to chat. So my talk today will be on feature geometry, and I will explain in more detail what I mean with that, and then what implications feature geometry has for model design in deep learning. So the talk will have two parts. In the first part, we will talk about one specific branch of deep learning, namely deep learning on graphs or graph machine learning. And in graph machine learning, as you might know if you have worked in this area, message passing graph neural networks are among the most popular architectures that are being used as graph neural networks. So they have been applied very successfully in many domains. There are still a few limitations that remain, and one particular area of challenges relates to situations or tasks where we have to encode long-range dependencies in the representations that the graph neural network learns. So for instance, if you think about a biochemistry application where the graphs that we perform a learning task on are proteins or other larger molecules, it's often important to capture dependencies between atoms or different components of the molecule that are not directly adjacent but further apart. And in order to capture something like that with a graph neural network and the representations that they learn, we typically need to build a deep graph neural network. Unfortunately, message passing graph neural networks suffer from instabilities as they get deeper. This effect is called oversmoothing. We will go into more detail specifically what that means. But as a quick initial definition, oversmoothing means that representations of two nodes that are dissimilar, so that should in principle be assigned or mapped to a distinct representation, become very similar to the point where they are indistinguishable as the number of layers grows. This phenomenon of oversmoothing is specific to message passing graph neural networks, but the kind of representational collapse that we see actually also arises in other architectures. There it is sometimes known as vanishing or exploding gradients. And in the first part of the talk, we want to zoom in a bit more into this phenomenon of oversmoothing, and we want to talk about how to redesign the base layer of a graph neural network such that those oversmoothing effects are mitigated and in fact can provably not occur. So in particular, we want to redesign the way graph convolutions are done. And graph convolutions are one of the most popular ideas for implementing message passing graph neural networks. So this will be the first part of the talk. And then in the second part of the talk, we want to go a bit more general. So not specifically focusing on deep learning on graphs, but on more general architectures. And here again, of course, feature geometry, the representations that a model learn is very important for their performance. And we want to, again, look at feature geometry sort of from the perspective of data geometry of certain structure that we have in the input data. But the tools that we want to use this time are tools from discrete geometry, in particular discrete Ricci curvature and an associated geometric flow. If you haven't heard about Ricci curvature and Ricci flow beforehand, don't worry. We will discuss that in detail. And then based on this lens of Ricci curvature and Ricci flow, we want to think about how characterization of data geometry with these tools allows us to get some insights into model design, and in particular a model design that ensures good performance. Okay, so that's the plan for today. But let me start with the first part and feature geometry in graph machine learning. So I'm assuming many in the audience have heard about message passing graph neural networks before. Of course, local at MIT, there are many experts. For instance, Stephanie Yigka's group has written many seminal papers on message passing graph neural networks. But just to get us all on the same page, let me give you a brief introduction. So a graph neural network, the representations that a graph neural network learns, you can think of as a joint embedding or representation of the adjacency of a graph, and any information that's given in the attributes. For the purposes of this talk, we will focus on inputs that have node attributes. So there's some vector with real entries that's associated with each node in the input. There are more general settings that one can consider where such attributes are also assigned to the edges, for instance. But for the purposes today, we focus on node attributed graphs. And then each layer in the graph neural network implements this message passing paradigm in the following way. So each message passing layer consists of two functions, an aggregation function and an update function. And it learns a representation for each node. So in the beginning, layer 0 or initialization, we assign whatever is given as node attribute as the initial embedding of each node. And then in each subsequent layer, we look at at each node's neighbors, and aggregate with some statistical aggregation function the embeddings of these nodes. So this can be something like element-wise average, or maybe a max. So there are different ways of implementing this, but it's some statistical aggregation. And then this aggregate is called the message, and that is passed together with the current embedding of the node into an update function. And this update function is a parametric function. Oftentimes, this is implemented as an MLP with trainable parameters. And then this update function gives us an updated or a new embedding of the node that basically captures information that was aggregated over the one hop neighborhood, right? And then as we stack layers on top of each other, then you can think of this as in the first layer, we capture information from the one hop neighborhood, in the second layer from the two hop neighborhood, and so forth. Now, where does oversmoothing come in? Due to the way this message passing is constructed, think about if we have a node that's in a very densely connected region of the graph. Then as we keep statistically aggregating information over the neighborhood, the messages will become very similar between close by nodes, right? Because the information that we keep aggregating is very similar. And if we keep aggregating sort of the same information, any distinguishing information that was there in the input is getting lost. So this is this effect of oversmoothing. And unfortunately, by the very design of message passing, this is an effect that's really hard to avoid. At least with the sort of standard way of how message passing graph neural networks are implemented. So let's take a closer look at this. So one very popular, or in fact, probably the most widely used way of implementing message passing graph neural networks is with graph convolution. So that gives you a graph convolutional network. And in that case, if we put together a set of layers of the form that we had just discussed with an aggregation function and an update function, then the function that the network learns looks something like this, where A is the adjacency matrix, X are the features, the node attributes, and then W are the trainable parameters. This kind of layer, just to point out here, is a permutation equivariant. So this means that it respects the fundamental symmetries of the graph domain. Right, in a graph, we don't have a natural order on the nodes. There's no easy way to say this is the first node, right? And if we were to permute the indices of the nodes of a graph, then the function that we learn, that our model learns to approximate, should not change. So that's why we want a permutation invariant architecture. And in order to achieve this, we need a permutation equivariant layer. And this is exactly what is achieved here. So very common way of implementing message passing graph neural networks. Now, how does oversmoothing arise here? And we want to illustrate this on a simple toy task. So suppose our input is a ring graph. So you have n nodes, and they're connected to two neighbors each in a closed ring. And then one task that we might ask the model to learn is to say, we mark two nodes in the graph, and then tell us what is the shortest path distance between those nodes. So in the most efficient way, what is the minimum number of nodes that we have to pass to get from one node to the other? So clearly, this is a task that requires understanding long-range dependencies, right? The two nodes might not be adjacent to each other, so this is clearly a long-range dependency that the network needs to encode here in its representations. So if we take a look at the learning dynamics here, so this equation that you see here is a very simplified way of writing down the evolution of the node representation here in layer L. And then here, the right-hand side, it's really sort of stripped away all the specific details. But roughly speaking, it looks something like this, the graph convolutions that we just saw. And then if we look at the dynamics here, we see for this specific example, but you can also observe it in other settings, that we have this representational collapse. So there's a unique fixed point of these dynamics, and that signifies this representational collapse that we see in oversmoothing. Now, what can we do to avoid this? So this is an unavoidable phenomenon, and the longer the long-range dependencies become, the worse this gets. So the idea that we propose in our paper is to replace those graph convolutions with a new convolution operator that we call unitary graph convolutions, because the parameterization is with a unitary metrics. In particular, we replaced this graph convolution operator that we saw earlier by this equation, with this notion here. Again, A is the adjacency, X are the node representations, and then U here is a unitary matrix. So that means a matrix that's complex valued. And U adjoint gives us the identity matrix. And then X here denotes the exponential map. So this is this term here. So notice that in this case, unlike with the standard graph convolutions, we have a convolution operator that's complex valued. So this is something that one has to keep in mind from an engineering perspective if we actually implement this convolution operator. There's a second parameterization of this that I won't be able to get into in this talk, that allows us to parameterize this with only real values, which perhaps from an engineering perspective is a bit more suitable. But we also have open sourced an implementation of this with complex valued operator, and you will shortly see in the experimental result that this also works quite well. So let's take again a look at this toy example of the ring task that we had earlier, and at the training dynamics. Right? Remember, for the standard graph convolutions, we saw this very clear representational collapse that signifies or illustrates the oversmoothing effect. Now, if we do the same experiment with the unitary graph convolutions, we see that the dynamics behave very differently, right? They don't have this unique fixed point. They kind of propagate in a wave-like pattern across the network. So there's no unique fixed point, and therefore also no representational collapse. And even as we make the network deeper and deeper, right, here we have a setting, for instance, that has 60 layers, which is extremely large for a small input like this. Even then, we see that it's always this wave-like pattern. There's no representational collapse. We can also make this more formal. I won't be able to go into the details here in the talk. But if you're interested, please take a look at the paper. This sort of analysis of the representational collapse and the fixed points that emerge in the dynamics is something that can be analyzed with respect to the spectrum of the graph that captures crucial topological and geometric information about the graph. And there is the so-called notion of the Rayleigh quotient that can be used to quantify oversmoothing. And one can show, while through this lens of the Rayleigh quotient, while oversmoothing always occurs in deep graph convolutional networks, this unitary convolution operator is the Rayleigh quotient is invariant under this unitary graph convolution operator, and this means that even as we make the network deeper, no oversmoothing can occur, right? It doesn't sort of amplify the oversmoothing effect as we get with very deep graph convolutions. So this is the sort of theoretical ideas behind this, and illustrated on a toy example. Oh, before we get to this, actually, one more note. So we in this part of the talk, we very much focus on graph machine learning and graph neural networks. But as I mentioned initially, similar instabilities, similar representational collapse is also known to occur in other architectures, and in particular in other structured or geometric architectures. So if you think of group-convolutional networks that implement symmetries as inductive biases beyond the permutations that are the inductive bias of graph neural networks, that in these structured architectures we also very often see similar instabilities, which are here more generally known as vanishing or exploding gradients. And this idea of the unitary convolutions to avoid those instabilities is something that can be made much more general than just graph convolutions. So in our paper, we actually define a more general unitary group convolution operator that could be used, for instance, also to define a unitary CNN, so a unitary convolutional neural network, and also many other symmetries that fit this framework. And then similarly here, we could build networks that are essentially as deep as we would like them without suffering from those instabilities. Okay, so now let me get to the experiments. Actually, let's take one more look at this simple toy example that we had before, and sort of course compare the performance of different architectures. So what we've seen before in the plots were the training dynamics, right? It was not the performance. In this plot now, you see the test loss, so the actual performance of the architecture. And the dotted line here on top is the trivial performance. So this is basically if the model would just randomly guess. And you see that, as we would expect from the theory, that many standard graph neural networks that are often based on some graph convolution do very poorly here. So we have a vanilla GCN, for instance, this is the standard graph convolutions that we saw earlier, just gets the trivial performance. Even if we put some common mitigation techniques that have been previously proposed for oversmoothing, such as residual connections, we still, in this particular task, don't get much past the trivial performance. There's one network here, the graph attention network, so that implements an attention mechanism for graph neural networks that gets a little bit better than trivial performance, but still performs very poorly. The only two architectures that can really learn this task and achieve perfect accuracy are the two variants of the unitary graph convolutions. So this is one parameterization with complex values and one with real values, as I mentioned earlier. So at least on the toy task, this looks quite promising. Let's take a look at an actual state-of-the-art benchmark. And the benchmark that we look at here is the so-called long-range graph benchmark. So this is a benchmark that was put together to specifically test how well a graph learning architecture is able to capture long-range dependencies. So exactly the setting where we expect the unitary convolutions to shine. The kind of tasks that you see here are graph classifications, so graph level tasks. So imagine that your input is a collection of graphs. Going back to our biochemistry example, those could be graphs corresponding to the chemical structure of certain molecules. Attributes, of course, are information regarding the specific chemical compound that is modeled, and then we might want to predict things like toxicity or how effective a certain compound if it's built into a drug. So those are graph level tasks where we assign or want to predict a label for each graph in the input. And then in the table here, you see in the first row, those are classical message passing architectures, including the graph convolutions, or GCN. And then we have a second plot here that implements other state-of-the-art architectures that you would see, or at least at the time when we wrote the paper, you would see at the top of the leaderboard for those specific architectures. Quite a few of them are transformer based. And then at the bottom here, you have the two variants of the unitary convolutions. And then you see here that we're very clearly outperforming the message passing graph neural networks, and that we're competitive with the transformer-based architectures. One note here for the transformer-based architectures is that for very large data sets, such as Coco and Pascal, and one really runs into scalability issues. Those are very large data sets, and graph transformers are notoriously hard to scale, whereas message passing type architectures are much more scalable to larger data sets. So certainly promising results on this benchmark. And then to show you a second set of experiments, those are for, this is a benchmark that focuses on heterophilic graphs. So heterophilic means that it's, or oftentimes in graph learning tasks, it's the case that the similarity structure in the attributes and the adjacency is pretty well aligned. So that means if two nodes are nearby, we can expect the attributes to be similar. But this is not always the case in practice. So for instance, one example here is an Amazon graph. So there the nodes represent buyers and sellers. And just because a buyer bought a product from a seller, that doesn't mean their attributes align, right? So in practice, we sometimes encounter these data sets where there's a misalignment between the similarity structure in the nodes and the adjacency. uniformity. And in this so-called heterophilic setting, we are particularly susceptible to oversmoothing. So this is why this is another setting where we expect the unitary graph convolutions to shine. And this is in fact also what we see here. Again, we have a block of message passing, standard message passing architectures, such as the graph convolutions, and we see here that the unitary architectures massively outperform them across data sets. Here we don't have a transformer block because those data sets are all quite large, and it's really hard to scale graph transformers to such large inputs. All right. Yeah. So this was the first part of the talk. And in I guess the interest of time, let me directly continue to the second part, and then we can take questions at the end. So a reminder, we had said now we want to look at feature geometry more general. We are not focusing anymore on symmetric or graph neural networks, but more general deep learning architectures. And we want to take this perspective of a discrete geometry lens, in particular, discrete Ricci curvature and associated Ricci flow. So let me start with introducing those tools, since I think those are maybe not everybody or few people in the audience have seen those before. So let me spend a little bit of time on this. So in order to perform this analysis that we want to do of feature geometry, we have to find a good way of characterizing data geometry. And curvature is a natural choice here, since it's an extremely central tool in differential geometry and also in data analysis as a geometric characteristic. It's so central because it really allows us to capture both local and global properties. Typically in differential geometry, or maybe your sort of intuitive idea of what curvature means probably looks something like what is shown in this little those little toy examples here. So the Euclidean plane, for instance, is a flat space, right? So it has curvature 0. You might know that if we're on a sphere, right, this would be an example of a manifold, of a space that has positive curvature, so in this case 1. And then you might have also encountered these sort of saddle-like structures. This would be an example of a negatively curved manifold. Now, in data geometry, we often work with a finite data set, right? We make the assumption that the data comes from some manifold, typically, but this data manifold is unobservable. So we can't directly use these classical tools from differential geometry. We have to think about equivalent notions that can work in a discrete setting, right? That can apply to a point cloud, that can apply to graphs, maybe more generally to hypergraphs or simplicial complexes. Let's say if you do topological data analysis. So we need something that works in the discrete setting. Now, unfortunately, in the discrete setting, we don't have a natural differential structure. So this means we can't sort of map one-to-one the definition from the continuous setting. We need alternative discrete notions. And in our setting, where we talk about, where we will also talk about geometric flows, those are typically associated, or curvature flows are associated with these classical notions of curvature, including Ricci curvature, and those are also naturally defined in terms of a differential structure. So the same sort of difficulty in defining those notions in the discrete setting arise here. And the way we want to go about this is to use curvature analogies. So basically what this means is that Ricci curvature or Ricci flow links to some properties in the continuous setting that or relates to other graph characteristics, other characteristics in the continuous setting that we already understand well in the discrete setting. And then we can try to find a notion that sort of maintains this relationship in the discrete setting to get a well-defined notion. Obviously, those notions won't inherit all of the classical properties of the continuous curvature notion. But if we carefully design and choose what notion we want to apply, we can preserve the properties that are really important to us in our particular application. This is just sort of very briefly, I wanted to state or mention what Ricci curvature means. So this curvature that we talked about here in these simple examples is a more general notion. So the most general way of defining curvature in the continuous setting is via the second fundamental form. The Ricci curvature is sort of one component of this more general second fundamental form that gives us a local notion of curvature. And you can basically think of, if you want to understand what Ricci curvature measures, you can think of that as a geodesic dispersion. So if we look at sort of local volume growth, the local growth of a geodesic ball, this is what is measured by Ricci curvature in the continuous setting. Now, if we want to have a notion in the discrete setting, and here we want to focus on Olivier's curvature, which is just one way of defining a Ricci curvature in the discrete setting. There are some other ways of doing this, but for the purposes of this talk, we'll just focus on Olivier's notion. And then remember, we had said we want to use a curvature analogy to define the discrete Ricci curvature. And the property that we want to mimic in the discrete setting in Olivier's notion is to look at the behavior of random walks on a manifold or on a graph. So in the continuous setting, why is this sort of a good property to look at? Is because there's a nice characterization of that behavior in terms of the Ricci curvature. So if we're in the continuous setting and we start two random walks at nearby points, then it is known that they will remain close by or draw together if the manifold has locally a positive Ricci curvature. And with high probability, they will draw apart, so diverge, if the Ricci curvature is locally negative. So this is a geometric fact that one can prove rigorously in the continuous setting. Now, in the discrete setting, random walks on graphs is something that is well studied and well understood. So there's a lot of theory that we can already build on, right? So to mimic this behavior that we have in the continuous setting, basically what we want is that if we start random walks at adjacent vertices, let's say U and V here, and then to model a random walk here, we typically would say the transition probability is maybe something like 1 over the degree of U for each neighbor, right? This would be a sort of classical uniform random walk. And then we can look at how these two random walks, one starting at U, one starting at V, behave, or if they stay close by or draw apart. And if we have a lot of joint neighbors, so if we're in a densely connected region of the graph, then it's very likely that the random walk will sort of jump from the neighborhood of U to the neighborhood of V and back and forth. So it will stay close by. And then if there are no joint neighbors or very few joint neighbors, then it's much more likely that the random walks will draw apart and sort of diverge into away from the other neighborhood. So this kind of overlap between the neighborhoods of the two nodes, this is really what controls or what should determine whether or not we assign positive or negative curvature to this edge. And this overlap is something that we can measure with optimal transport. So by looking at the Wasserstein-1 distance between the two uniform measures that are induced by the uniform random walk that we're considering. And then Olivier suggests to say that the Ricci curvature is 1 minus this Wasserstein 1 distance between the measures divided by the shortest path distance. So in our case, for two adjacent nodes on an unweighted graph, this is just 1, right? So if there's not a lot of overlap, this Wasserstein 1 distance is going to be large, and then 1 minus something large is negative, right? So we have exactly this behavior that we want to model from the continuous setting. If there's a lot of overlap, the Wasserstein 1 distance is small. 1 minus something small gives us something positive, and that's exactly the behavior that we want, right? Okay, so let me briefly, since we're talking about data manifolds, so sort of going from the discrete to the continuous setting, let me say a little bit more about how we can model that, which is also what we want to use later on in the talk. And then also how this notion of Ricci curvature that we defined here, how that relates to the sort of actual or classical Ricci curvature on a manifold. So one nice tool to sort of interpolate the discrete and the continuous regime for a point cloud that was sampled from a manifold is to construct geometric graphs. So let's say we have our point cloud. This is all we observe, right? The data manifold from which those were sampled is unobservable. We know nothing about that manifold. We just know it's there. If we have our point cloud, we can assign each point a node in our geometric graph, and then we draw an edge to all nodes that are within an epsilon distance, right? So we construct epsilon balls around each point and then draw the corresponding edges. And then as we vary epsilon, we get a family of geometric graphs that sort of capture geometric information at different scales. As we look at this family of geometric graphs, we can ask a lot of geometric questions about what we can measure on those geometric graphs in terms of the sort of true geometric properties of the underlying manifold that is unobservable. In particular, we can look at so-called continuum or discrete to continuum limits. So in the limit, of course, we would have an infinitely large sample. And then as we let epsilon go to 0, we would sort of approximate better and better the true underlying data manifold, right? I should note that so various geometric characteristics have already been explored in this setting. So for instance, questions like if I measure distances on this geometric graph, does that tell me something about the true geodesic distances on the manifold that has been analyzed? If I look at the graph Laplacian, does that tell me something about the Laplace-Beltrami operator? So those kind of questions have already been asked and studied in discrete geometry. Here we're looking at what happens to the curvature, right? If we measure Olivier's curvature on the geometric graphs, can we learn something about the Ricci curvature of the underlying manifold? And in fact, we can. So we show two types of consistency results. We first show that in a local sense, we can locally approximate the curvature in the neighborhood of the point on the data manifold. We can do this not only in the continuum limit, but in fact, we can give non-asymptotic error bounds. So we can specify to what accuracy we can approximate the true Ricci curvature for a sample of size n. There's some technical details that I won't be able to go into here, but the approximation, the quality of the approximation here also depends on things like the dimension of the manifold, also this epsilon neighborhood radius, so that the scale of the geometric graph has to be chosen very carefully. And in the paper, we provide more guidance on that. But basically, what to take away from that is that we can locally approximate the Ricci curvature around our sample point on the data manifold, and we can get some bound on the error that we might incur in this procedure. We can also give or learn a global lower bound on the Ricci curvature of the manifold in this formalism. Again, here that depends on the quality of the approximation depends on things like the dimension and is conditioned on a careful choice of the scale. But what we can say is that if the manifold has a Ricci curvature that is lower bounded by some constant, then we can learn that constant up to some error from a finite sample using Olivier's Ricci curvature. So what this basically implies is that even though we have built Olivier's Ricci curvature only via a curvature analogy that is sort of not designed to capture all aspects or all geometric properties of the underlying Ricci curvature, we have a tool that allows us to basically recover a lot of information about the Ricci curvature on the underlying data manifold, even if we can't observe it. And before we get to the application or why this sort of tool allows us to learn something about feature geometry, let me just put one more slide here to understand or to briefly define the Ricci flow. So the Ricci flow is associated with Ricci curvature. It's just like Ricci curvature, a very central tool in differential geometry. Was introduced in the 1980s by Richard Hamilton, and it basically tells us something about how the metric of the manifold involves under a flow that is in a sense guided or dependent on the Ricci curvature. Now, in the discrete setting, Olivier actually, and even in the original, one of the original papers, when he introduced his curvature, also proposed a discrete analog of the Ricci flow that basically gives a similar definition of a flow in terms of the shortest path distance, which is sort of the analog of the metric, the geodesic distance on the manifold, and again guided by the curvature. I should note here, unfortunately, there's not this consistency or continuum limit that we have for the curvature. This is something that has not been proven for the flow, and I think would also be very difficult, maybe impossible to do. For some sort of technical reasons that I can't go into here. But nevertheless, this discrete flow has been studied quite extensively in the discrete geometry literature and has also found applications in graph machine learning. For instance, we had a paper last year that looked at how to use this idea of discrete flows for clustering on graphs for community detection. So it's nevertheless a well-studied tool. Now, let's now actually go to the feature geometry setting. And let me just briefly sort of define the setting in which we're working here. So we look at a very sort of general class of neural networks, standard feed-forward neural networks that may or may not have a nonlinearity. If there's no nonlinearity, of course, we call this a linear network. If we have a nonlinearity, you can think of this as a ReLU activation. And then how we want to study feature geometry. So here we again use this tool of the geometric graphs that we had already discussed earlier. For the input data, of course, we can find an approximation of the data manifold in exactly the way that we had constructed geometric graphs before, right? So if, let's say, we have a binary classification problem, so sampled from two classes, we can think of maybe the manifold looks something like this, and then our geometric graph would approximate it in as something like this. Okay, so that's the picture to have in mind. And then we sort of look at how these samples are transformed as we sort of proceed see it throughout the layers of the network. And then based on that, we can, based on those transformed samples, we can again construct families of geometric graphs. And we can say that those sort of implicitly measure the feature geometry. You will see quite a few experiments. So just to show you what the data sets are here. So we work in this binary classification setting. So this really, while this is a sort of a schematic figure, this is really the picture to keep in mind. So we only look at settings where we have a binary classification task. And we look at synthetic data that is sampled from some low-dimensional manifolds of interesting geometric structure. And then we also look at some real-world data. So here we use MNIST, Fashion MNIST, and CFAR. And to preserve this binary classification setting, we always pick two classes at a time. And we trained over 20,000 networks. And by analyzing the data that we generated in those experiments, this is what those results that I'm going to talk about are about. So in order, what we want to do is to take a look at the evolution of the feature geometry by measuring the geometric properties of those geometric graphs that we have constructed from the data, so the reconstruction of the data manifold, as well as the geometry of those transformed samples. And this basically gives us a proxy of how the geometry of the data manifold transforms throughout the network. So, and this gives us a means of analyzing the feature geometry. So the tool, of course, here that we're using will be Ricci curvature and this discrete Ricci flow that we saw a few slides ago. So the way we want to the lens we want to use here is to look at the average change in the distances under those transformations. And this sort of gives us a way of, or this measuring those changes, we can then compare to what we would expect under the Ricci flow. And if this aligns well, that gives us empirical evidence that the kind of transformations of feature geometry that we're observing mimic something like a Ricci flow, or are in a sense guided by Ricci curvature. So the average changes in the distances. Here, we're talking about the shortest path distances on the geometric graphs as a proxy for the geodesic distances on the underlying unobservable data manifolds. So this is captured here in this eta L, where L is the indexing the layers. And then in order to measure how well that aligns with the expected behavior that we would observe under a Ricci flow, we define these what we call the local Ricci evolution coefficients, which are essentially a Pearson correlation between this average change in the distances and the change of the distances that we expect under curvature. So this is based here on Olivier's curvature. In the paper, we also look at some other notions of curvature, but for the purposes here, just think of the Olivier curvature that we had introduced earlier. So if we look at the data from our experiments, I should say we expect a negative correlation if this alignment that we would expect under Ricci flow type evolution of feature geometry, we expect negative correlation coefficients. And we see here that across data sets, so here you see some samples of the results for the real world data. Similar observations can be made for the synthetic data. You see that we have always negative coefficients, and then in brackets here you see the sort of the percentage of nodes, of points in the data set at which that was observed. And you see that that is always the case for the vast majority. So what we could get from this is basically strong empirical evidence that the evolution of the feature geometry does exhibit a behavior that's resembling a Ricci flow on the underlying manifolds. So this is sort of an illustration of kind of what we expect. So if we right, if the network learns representations that separate the two classes, right, this is expected to happen if the model can learn a good binary classifier, then we would expect to see this sort of behavior in the feature geometry. And this is also what we would expect under the Ricci flow. So if we apply a Ricci flow to a manifold like this, then we would get this kind of separation. And then, of course, on the corresponding geometric graphs, this is also the kind of behavior that we expect to see. And beyond this empirical evidence that we gathered from our experiments, there's also one can give theoretical justification for this behavior. Basically, reusing this theory that we developed, and there are also papers by a few other people on this for clustering on graphs or community detection. Namely, if we have an input graph like this, maybe forgetting for a minute that it's a geometric graph, but if this is our input graph and we want to cluster the nodes into two classes, we can apply community detection. And Ricci flow-based community detection can, in fact, has exactly that behavior, that it sort of cuts some of the edges between the communities, and sort of pushes the nodes within each class closer together, shortens the distances between them, and we have this sort of evolution that two sort of separate components of the graph emerge. So this gives additional sort of justification why we would expect this behavior, and why we would expect that if the network learns a good binary classifier, that the transformations of the feature geometry exactly align with this behavior. This is one more sort of analysis of this emergent structure that is not using Ricci curvature, so that we have sort of a neutral way of quantifying the emergence of community structure. So here we looked at we looked at those trained networks across the training procedure, constructed the geometric graphs, and then measured the modularity and the normalized cut. Those are both two ways of measuring how much community structure there is, so whether the transformation really is of this form. And we see that this community structure really emerges sort of as we go across the layers. So this is another sort of empirical evidence that this behavior is in fact what we expect it to be from the Ricci flow. Now let's sort of, having observed this phenomenon, let's think a little bit about how that relates to certain choices that we might make in model design. So the first insight that we can get here, or for which we can, this is an observation that's of course been made before, but where we can get a geometric insight here, is the essential role of nonlinear activations. So it is well known that linear networks can not always find good binary classifiers. In particular, for some of the examples that we're looking at here, for instance, those low-dimensional manifolds that just go quickly back to this. So here there's, in order to learn learn a binary classifier in settings like this, the model needs to learn nonlinear structure well. And it's well known that this is difficult to do for a linear network that's been empirically observed. Here we give some theoretical analysis of why those nonlinear activations are really crucial from the perspective of feature geometry. Namely, we show that without the nonlinearity, the kind of transformations that we are learning are incapable of rewiring or changing the structure of the geometric graph in a way that would allow to separate the communities. But as soon as we put in a nonlinearity, let's say a ReLU activation, then the maps are capable of learning a rewiring of the graph, are capable of capturing the community structure in the geometric graphs, able to capture the underlying data geometry in a way that allows to successfully learn a binary classifier. What I put here are just informal statements. You see much more details in the paper if you're interested. And just to give a few more results here that also link to things like the design of the network or the design of the training protocol and how that relates to feature geometry. So in this analysis of the data here, we look sort of throughout the training process across epochs. And measure the local Ricci evolution coefficients as well as the accuracy in terms of training and test loss that we observe. And here we see that. So remember, local Ricci evolution coefficient is what we expect if we have Ricci flow type behavior. And this coefficient gets more negative sort of as the network learns. And then once the accuracy stabilizes, then also the correlation coefficients are stabilizing. So this really sort of gives evidence that and you see this here for one data set, but this was something we observed across our experiments. You see that really as the network learns, we have this Ricci flow type behavior. And then once the network has learned to capture the structure that is necessary, then we also see that this Ricci flow type behavior stops. We see here in later epochs, if we continue to train, that the local Ricci coefficient actually increases. We think that has something to do with overfitting that we expect to happen if we just keep on training. So from a model design or training protocol design perspective, we think that one promising future direction is to maybe think about how this theoretical lens could give us a principled stopping criterion. But in this paper, we didn't get to explore that, but I think it's a interesting direction for future work. And the very last set of experiments that I want to show links back to model design, namely to thinking about what is a good number of layers to choose, right? How deep should we make our model? So here we look at again the accuracy and the Ricci evolution coefficients, but now across layers, not across epochs. And again, we see that sort of for shallow, in the shallow case, it sort of helps, or as we make the network deeper, the Ricci coefficients are decreasing. So again, indicating that we have this Ricci flow-like behavior that learns to capture the geometry. And this coincides with an increase in the test accuracy. And then at some point, the test accuracy, as we make the network deeper and deeper, the test accuracy drops, sort of once we're past the optimal number of layers. And this also coincides with an increase again in the Ricci coefficients. So basically the point where this Ricci flow type evolution of the feature geometry is broken, and the network starts to overfit. And again, here we see across data sets this sort of nice alignment with the evolution of those coefficients across layers, and the test accuracy that we see. Again, here, one possible future direction would be to use this geometric lens to think about what's an optimal number of layers to choose. This is something we sort of just empirically explored a little bit in this paper, but where I think more work could be done, and maybe some nice design principles for different types of architectures could be developed. Okay, so this is all I wanted to say for today. So let me just briefly summarize. So in the first part of the talk, we talked about unitary graph convolutions and how that's a nice way to build stable graph neural networks that provably don't suffer from oversmoothing, but can encode long-range dependencies well. And if you're interested, please take a look at our paper. And then in the second part of the talk, we discussed feature geometry through the lens of discrete geometry using discrete Ricci curvature and discrete Ricci flow. This paper is currently under review. It's on arXiv. And then I also made a quick excursion into continuum limits of discrete Ricci curvature. And this paper is also under review, and you can find on the arXiv. So these are the my co-authors for this work, some collaborators in Germany and at the University of Wisconsin, and then former postdoc Boba Kiani and my group who led the work in the first part of the talk. He's now a faculty at Bowdoin, and then Lucas is a PhD student at Harvard. And with that, thank you very much. Oh, one last note, my group is hiring both PhD students and postdocs. So if anybody is interested, please feel free to email me. Thank you.
In-room mic, and hopefully the mic and laptop will pick that up.
Yeah, am I audible? Not sure. I just figured out.
We have a question.
Yeah, I have a question. Yeah, so my question was regarding the first part where you mentioned you use the exponential operator and then there's no oversmoothing. So I was interested to know if the only requirement is that it doesn't have a single fixed point, or whether other considerations in choosing that specific operator.
Yeah, that's a great question. So if I understand correctly, you're kind of asking for the inspiration of choosing this particular
whether there are other choices as well, or like whether there were considerations about other types of operators.
Yeah. This is a great question. So as I briefly mentioned, there are many different ideas that have been proposed to overcome oversmoothing. So this idea of using unitary operators actually goes back far into the literature, at least 20 years. Back then, people experimented with unitary operators in RNNs. So for very different type of architectures. So if you go back in the literature 20 years, you find unitary RNNs. For sequence modeling. And then the sort of instabilities that arise there are very similar to what you find with oversmoothing in graph neural networks. So we kind of made this connection between those sort of old techniques, and then mapped this over to graph neural networks initially. And then, as I briefly mentioned, you sort of have similar issues with more general group-convolutional networks. So then we channelized our unitary graph convolutions to those settings as well. But yeah, this is where the inspiration came from, basically making a connection to these old ideas in the RNN literature.
Okay, the next talk starts in 10:30, so we have time for maybe one or two more questions. Okay, well, I guess we can thank the speaker again. And yeah, our next, get ready for our next talk.
Thank you.